Hello everyone, welcome back to the Ultimate Sats Guide. We are taking a look today at geometry questions. It's being requested a lot by you guys. Look, it's here, it's happening. Let's dive straight into some questions, how to answer them, and what could possibly come up in this Sats paper when it comes to shape and geometry. Now, this is probably the most simple question I could find. It's from the 2023 paper. And when I say simple, I mean it's geometry at its core. This is just geometry. Do you know the vocabulary of irregular and regular, pentagon and hexagon? Have a go. I'm going to tell you what they mean after. Now, I'm hoping you worked out you're supposed to match them up and not just know what the words mean. Okay, so you're going to have to match up the pictures here to what these words mean very quickly. Irregular and regular are ways we can describe 2D shapes. They're the flat shapes we see, 2D polygons in particular, 3 or more straight sides. Regular means that all the angles in this inside the shape and all the lengths of the sides are the same. Irregular simply means that they're not. The lengths of the different sides could be all different. The angles could be all different. And what we tend to see people say is regular are the normal shapes. I get what you mean. They're the shapes that we see a lot of, but then it's not good vocabulary to say. We should say regular. And pentagon is 5. Hexagon is 6. Very easy way to remember for me is that hex and 6 both have the X at the end, which helps me to remember. Simple. So irregular pentagon. We want a 5-sided shape where the sides are different lengths. Straight away I can see it's this one. Okay, so I know the bottom side is longer than these two sides on the edge, so it must be irregular. Irregular hexagon. Well, I want a 6-sided shape now, where the sides are different lengths. It's this bottom one. Quite clearly, this is a short length. This is a long length. Regular hexagon, so the only 6-sided shape left up here, and regular pentagon. As simple as that. It does get harder, I promise. Now we're moving to 3D shape. 2D shapes we just looked at here, they're flat shapes that don't have any depth. A 3D shape, I know it's on paper, or in your case, a screen, but it's got dotted lines to show that these edges are further back. And we can kind of see here, it's almost like a pyramid with the top cut off. So here's a drawing of a 3D shape. Complete the table. Faces, vertices, edges. Have a go and I will tell you what they mean after and what the answer is. So when it comes to 3D shape, faces are actually the 2D shapes that we build the 3D shape with. In this case, we can see a face at the front, can't we? This quadrilateral, this 4-sided shape. So how many faces does this have? It has 1 at the front, 2 at the side, 3 at the back, and then 4 on this side. So 4 going round. We have a face at the top, which is 5, and a face at the bottom, which is 6. It's all about visualizing. It's like spatial reasoning, this one. Your question at the end, by the way, is a really tricky question. Stick around for it. Number of faces then is 6. Number of vertices. Well, what is a vertice? I think it's best to go to edges first. I'll explain what a vertex is after. So edges at the end are long edges. It's basically what it says in the name. They join together the vertices. So they kind of depend on each other, these two, when it comes to the definition of them. So the edges are these lines that we see here. So we have 1, 2, 3, 4. We're basically thinking if we were to build this shape using sticks, how many sticks would we need? We need 4 for these. We need another 1, 2, 3, 4 at the top for that square. And we need another 4 at the bottom for the square at the bottom. So we have 4 plus 4 plus 4. We have 12 edges. Now, what's a vertex? Vertex is 1. Vertices are plural for more than 1. A vertice, or vertex rather, is the joining point of the edges. So in this case, we have 1, 2, 3, 4. And what I think here is, okay, number of edges is how many sticks we'd need. Number of vertices is how many blobs of blue tack we'd need to hold them together. Well, we need 4 at the top. And we need 4 more at the bottom. So they're the vertices. We have 8 vertices in total. So best way to think about this for 3D shapes is edges, how many sticks would you need to build the shape? Vertices, how many blobs of Play-Doh or sticky blue tack, I don't know, whatever it's called, sticky stuff, blobs, Play-Doh, would we need to join them together? You could think of spaghetti sticks and marshmallows if you've built anything with that before. And faces are the 2D shapes that we're left with at the end, around the edges, around between the edges rather. So again, that's basic 2D. That's a basic 3D question. We just need to know those. If you don't, you need to learn them. Simple as that. Here's where we kind of step a bit more into the big boy questions. So ABC is a triangle. What are the coordinates of point C? Coordinates come under geometry. Okay, I'm not going to tell you how to do coordinates. I'm not even going to pause the video. I'm going to let you have a go right now. What are the coordinates of point C? So find point C here. How would we write these coordinates? We're even given the brackets and the comma. The only thing you're going to have to do is think, do I go across the x-axis first or up the y? Well, guys, listen, if there's something you're going to learn from this video, it's that you can only, you will play Xbox and then have your yogurt. Okay? Yeah, you'll play Xbox, then you have your yogurt. What on earth are you talking about? Well, we go across the x-axis along the corridors. So we go across here from 0, 0 to 6. I played my Xbox, x-axis, get it? And then I'm going to go up and have my yogurt, the y-axis, 2 to get to C. The answer is 6, 2. Along the corridor, up the stairs. Have your Xbox, then have your yogurt. Simple as that. Okay, so what about when we have a grid that looks like this with negative numbers? What is the coordinate of the missing vertex? Wait, what? What do you mean missing vertex? Well, you need to read this question carefully and have a go. This is multi-step here. See what you can do. Now, what's really interesting to me in this question is that it's asking for a square. And we spoke about this earlier when I said regular shapes. Regular shapes, it's just the normal shapes. It's what we always see. Okay, well, you're used to seeing a square like this. Okay, with a flat side across the bottom. This clearly is not that, is it? Because it's going to draw a square in this grid. So these points join together like this. Now, clearly, this is not the start of a shape that I see regularly like this. What's happened here is this square has been rotated 45 degrees to sit on a corner point. So 3 of the vertices are marked. We have one here, one here, one here. What's the coordinates of the missing vertex? This is a 2-step problem. Where would the last vertex have to go to make a square, a perfect square? And then we've got to write it as a coordinate. So this is how we elevate coordinate questions when it comes to SATS papers. How does it make it more tricky? Well, here's the easy version. What's C? Okay, cool. Here's how we make it harder. Make a square. By the way, it's not a regular square. It's not a square you normally see. It's on its corner. And then you've got to do some coordinates with negative numbers. So let's solve it. A square has same length sides. So what you could do is turn your paper in real life and make it look like a square. Simple as that. Or you could notice that look what's happening here. We go 1, 2, 3, 4 up, 1, 2, 3, 4 across. So we're hitting the exact diagonal and we're going through the corners of each of the small squares just like this. So up here, we need to come back down 1, 2, 3, 4 right there. And the way we can check this, let's go and finish this square off. Again, right through the corners, 1, 2, 3, 4. Yes, each one is going through 4 squares directly through the corners. And what you can see here, the big square now, if we were to turn your head that way, you can see, yes, look, it's a beautiful square. That's not the end of the question though. What is this one here? Remember, you can play Xbox and then have your yogurt. So we start always at 0, 0. No matter what coordinate grid we're in, we start at 0, 0. And we have to go along the x-axis. Just this time, we're not going 1, 2, 3, 4 up towards the right. We're going down towards the left. But it doesn't matter. We still do the x-axis first. -1, -2, -3. So -3 is the x-axis reading. And then we go up still into positive numbers for y. But we just go up 1. So the missing vertex is -3, 1. Multi-step problem there, and it's how we make coordinates tricky. This came up in the 2018 paper. This could come up in the paper that you're about to sit. Could happen. I then saw this and I thought I've got to include it because what we're seeing here is really easy coordinate question. Quite tricky coordinate question. One of the hardest coordinate questions I've ever seen. Pause the video, have a go, and I'll tell you how to answer it afterwards. See what you get. So we need to work out the coordinates of P. But look, there's nothing along the x-axis. There's nothing along the y-axis. There are no squares for us to count along. The only thing we have to go off of is this data here. These two rectangles are identical. The length of each rectangle is 3 times the width. And these coordinates that we're given right here. So this is 0, 1. This is -2, 8. So here's what we know. If this is -2 across, because it says -2 first, we know the length, we'll call this the width rather, is 2 squares. Okay, we know that. So actually we know that this here is 2 squares long because these rectangles are identical. Okay, that's kind of useful. What else do I need to know? Well, the other important thing, vital in fact, is that you know that this is 2 So let's just label that because opposite sides of rectangles are the exact same. And then we're given 8, which means we go 8 up. From here all the way up is 8. So we know that this little gap here plus the extra is going to give us a total of 8. So this has to be less than 8. The whole length of the rectangle has to be less than 8. Well, we don't even need to guess here because look at the second sentence. The length of each rectangle is 3 times the width. Well, we know what's 3 times 2. It's 6. So we know for a fact straight away now it's 6 across to get to P. We start at 0 and we go across 6 because 2 times 3 is 6. 3 times the width. But how tall up do we have to go? Well, we don't need to work that out either because look, we know this point is 0 across and 1 up. So we have a jump of 1 and then we have another jump of 2, which we know is the width of the rectangle. 1 plus 2 is 3. The answer is 6, 3. We go across 6, we go 3 up, and we've worked this out solely from these two sentences and the given coordinates. One of the trickiest questions we've seen. If you manage to go along with that, never mind get the answer, you're in a good position. If not, it's all good practice. And how could I not include this classic coordinates question? What are you thinking? What do you mean classics? Amongst teachers, this is a classic question, okay? Because once more, what we've seen is the highest level of coordinate questions do not have any rulings or markings along the x and y axis. We're simply given a shape and some coordinates and some information. I want you to have a go at this, see if you can get there. I'll tell you what the coordinates are for B and D at the end. Okay, so let's just firstly isolate the x-axis, okay? So what is this point here where the rectangle starts? How far across do we go? Well, luckily we're given it. It's 25 because A is 25 across and 30 up. So we know this is 25. Now, what else is vital to understand is that this C here, point C, is the center of the rectangle. So whatever this is here on the x-axis, which we know is 40 by the way, because we're given it, that's halfway across. So do you know what we can do now? Because we have the start of the rectangle is 25 on the x-axis, halfway is 40, we can actually go to the end. Because whatever we do from 25 to 40, if that's halfway, that's adding 15. We add 15 again, and we know the end of the rectangle is 55. So B and D both have a value of 55 when it comes to the x-axis. Now, okay, that's all well and good, but what can we do for y? Well, it's the exact same, okay? Because look here. Let's go to A, for example, and come across. What is the y value of A? Well, we're given it 25 across and 30 up. So this is 30. By the way, it means we can solve B straight away. B is 55 across and it's the same height as A, so it's 30 up. So we have 1/2 of the answer straight away. What about D down here? Well, we're going to do the same logic as before. If this is 30 at the top and then C is halfway, and we know that's 22 on the y-axis, 40 across, 22 up, well, guess what? To get down to D, we just need to do the same jump again. 30 to 22 is a jump of 8. We're going to take off another 8 and we're going to get to 14. That means that D is 55 across and 14 up. At no point was I just reading off across and up. I wasn't doing it. I had to work it out based on all of these clues. This is the ultimate version of a coordinates question when it comes to geometry. We've got shapes involved, coordinates comes under geometry. This is as hard as it gets. Fantastic if you're listening along and kind of understanding. I wanted to move on now to symmetry, another big part of geometry. I'm not even going to help you out here. All you need to know is you need to draw the lines of symmetry. Also, I've not got a ruler. Okay, I'm not got a ruler. You've got a ruler if you did a real thing. But where are the lines of symmetry? Where can I draw and cut this shape in half so that if I fold it, it perfectly matches up? How many can you find? We'll see after. First one, most children will get this one. We're going to draw a line down the middle because if I fold it down the middle, all of these will match up perfectly. This corner will match with this corner will match with this corner. There'll be no overlaps at all. That's what you need to think about with symmetry, okay? So here I've got the top of a Pringles lid, okay? I like my Pringles. I've got a Pringles lid. This circle has symmetry because if I fold it in half, there's no overlap, okay? It fits perfectly, okay? So that has a line of symmetry down the middle. You can kind of see it there in the light. However, sometimes if we fold, in this case, let's say I take my circle again and I try to do a line here. This, you can see in my little box, is not a line of symmetry because look, there's a huge overlap, okay? So for it to be a line of symmetry, there will be no overlap. The other line of symmetry is across here. So there are two lines of symmetry. You might be tempted to draw a line of symmetry going like that. No, do not be tempted to do that, okay? In fact, look, I've ruined my shape now. The dotted lines are the symmetry lines. This bold one here does not work. And you can prove it. I'm going to prove it right now. I've got a piece of paper. It's a rectangle. Look at my camera down the bottom. If I fold it in half this way, it lines up perfectly. If I fold it in half this way, it lines up perfectly. However, if I try and fold the rectangle diagonally, look what happens. It's not perfectly symmetrical. It has overlaps. It does not work. This rectangular shape cannot go across. The only lines of symmetry are vertical and horizontal. That's it for this shape. Okay, that is it. So, leading on from symmetry is reflection. Okay, so in this one that we just looked at, there was symmetry inside of a shape. Here we're given a shape and we're said, okay, as ABC, the triangle. She's going to reflect the triangle on the y-axis. Imagine the y-axis is a mirror. What would we see on the other side if we flipped this over? Have a go and I'll show you how to do this right every time after. So to get this question right, okay, what you need to do is very simple. Get to each corner and do one at a time. So see how far away from the mirror line is it? 1, 2. So now we go from the mirror line over to the other side. 1, 2. That's going to be C. Do the same for A. 1, 2, 3, 4, 5. So now we're at the mirror line. We go 5 over. 1, 2, 3, 4, 5. That's going to be my A. And when it comes to B, we know it's directly below A and in line with C. So B is going to be right here. We could do the counting again if we wanted. 5 over, 5 over. But now with a ruler, you would, I'm doing it freehand, you would then draw this shape perfectly. This has been reflected. You'll notice it does not look the exact same because that's what happens when we reflect a shape. It moves over. Okay, if you want to test it, get a mirror and see what happens when you put a triangle next to it and look what you see in the mirror. It should look exactly like this. So with that in mind, where would this shape go? Trickier, but use my technique. You'll get it right. Now, it's not a traditional shape that we'd see. It's not a triangle, okay? It's not a quadrilateral that we're used to seeing, a square or a rectangle or anything like that. So we need to go to each corner. 1, 2, 1, 2. I'm going to match that up here. Let's go to this one now. 1, 2, 3, 4. 1, 2, 3, 4. So we're going to line that up. Now let's go to this one, this vertex. 1, 2, 3. 1, 2, 3. Now this is really important. If we join up as we go, we won't get confused. Let's go to this bottom one now. 1, 1. Okay, now we just draw a line. And we can kind of see, look, it's reflected already. Go to this bottom right. 1, 2, 3, 4. 1, 2, 3, 4. Join it up. And then we've just got a straight line down the side. You use a ruler. Be much better and neater than mine. But this would get you the mark. Because you've been systematic and you go through every single vertex one at a time. Please use a ruler. Don't do what I'm doing. And just do it freehand. Use a ruler. Okay. I love this one. We're going to kind of amalgamate, put everything together now. So first question, Laura plots another point on the grid at -1, 2. So we looked at coordinates. Can you go -1, 2? Put a point where it would be and joins the points to make quadrilateral. What would this look like? Well, I want you to point on the screen right now where I'm going to draw the point in 3 seconds. -1, 2. 3, 2, 1. Start at 0, 0, -1, and then 2 up. 1, 2. It's going to go right here. Well done with your fingers there. Give yourself a pat in the back. Then we're going to join them up with a ruler. Obviously, you'll use a ruler. And we have a shape like that. Okay? Simple. And again, this is where we can add another question. So you've already done this now. This is very common when it comes to doing geometry questions. You have to do something first and then do something else. What we have now is Lara then translates. This is new language. Translate just means move from one place to another. Like when we translate the word hello into French, it becomes bonjour. It still means hello, it's still the same meaning. In this case, it's going to be the same shape, but it's in a different place, okay? So Lara translates the quadrilateral 4 squares to the right. Where would it end up? Have a go. See if you can tell me exactly where it would be, then I'm going to draw it. Okay, so what we do here, the same thing. Corners are your friends. Go to each vertex and go 4 squares to the right. Bottom one. 1, 2, 3, 4. Here. 1, 2, 3, 4. Join it up as you go. It's the best practice. Now this one. 1, 2, 3, 4. Each time we're moving 4 over. Okay. Top left here. 1, 2, 3, 4. Join them as we go. And then we've just got to join up these last two. And you'll notice it's the exact same shape. You'd use a ruler, remember? And it's been translated 4 squares across. Because each corner we've gone to and moved 4 squares across. That is the best way to do it, I promise you. Go corner to corner, join up the shape as you go. You'll get it right every time. This is the ultimate question now. This is the ultimate movement. All I will say here is draw the new triangle on the grid after each transformation. So you have a few to do. Where do you think the triangles would end up if you translate the shape 7 units down? Where would that first triangle be? And then if you reflect it in the y-axis, where would it be? So we're putting together everything we know now. This is classic SAT question from 2022, a real one. Where would it end up being? Have a go. So first one, translate the shape down 7 units. Go to the corners. 1, 2, 3, 4, 5, 6, 7. Boom. Next one. 1, 2, 3, 4, 5, 6, 7. Boom. Next one. 1, 2, 3, 4, 5, 6, 7. Done. Okay. But here, look, draw the new triangle after each transformation. You need to draw this triangle in to get a mark. Okay. You cannot just go to the next transformation. You have to draw this in first. Cool. Secured. Got the first bit. I'm even going to tick it. Now reflect the resulting triangle, which is the new one, in the y-axis. We're not reflecting this one. We're reflecting the new one in the y-axis. So the y-axis is here. Don't be put off by the fact these numbers are in the way. This still counts as 1 square. So let's start with this corner here. We've got 1 to the y-axis, and then we go 1 out, which is just going to be right here. This put a lot of people off in the real test, by the way. Don't be put off by it. Down the bottom, 1. So we go 1 across from y. And then here, this last vertex, 1, 2, 3, 4, 5 from the y-axis. 1, 2, 3, 4, 5 from the y-axis. Are we done? No. It says draw the new triangle. At the minute, we've just got corners. We're going to draw the new triangle in, just like this. Then we get full marks. Look how, this is what the SATs does. It puts everything into one question. So you've got to get it all to get all the marks. It's important you're really paying attention, guys. Oh, circles. This is just a vocab check, okay? So I'm not going to pause it or anything. Can you already match them up? Here are some diagrams showing parts of a circle. Match each diagram with the name of the dashed line. So we just need to know how circles are made up. As part of geometry, this is a year 6 objective. Which dotted line shows the circumference? Well, circumference is all the way around the edge of a circle. That's called the circumference. It's like the perimeter, but we have a special name when it comes to a circle. The diameter is all the way across a circle through the center point. Has to be through the center point to be the diameter. And the radius is linked to the diameter. It's just half. So it's from the center point out. Simple as that. That is what we need to know. If you don't know those, screenshot this, learn them. Okay, you have to. So let's use this language now. The circumference of this circle is 60 centimeters. We just said the circumference, by the way, was all the way around a circle. So all the way around this circle is 60 centimeters. What is the distance from A to B? The key here is this little square. What does that mean? Have a go at this question. I'll tell you how to do it after. So there are loads of facts we need to know here. Angles have everything to do with geometry, so these are linked together nicely. Firstly, this little square here is a right angle, which is 90 degrees. Why is that important? Well, because what we need to know when it comes to a circle, if I draw my dotted lines in, another 2 radius here, a circle is 4 right angles. The total degrees in a circle is 360 degrees. So a right angle is 1/4 of a circle. So if we've got 1/4 of the circle from A round to B, but we need to work out 1/4 of the circumference. We've got 1/4 of 60. If you know your time, this is going to be really easy. If you don't, you're going to take 60. You're going to divide it by 4, so it's in quarters. You're going to get 1 lots of 4 and 6, with 2 left over. 5 lots of 4 and 20. 15 centimeters is this chunk from A to B. Because the next one would be another 15, another 15, and another 15. 4 15s are 60, which is the total circumference. Well done if you managed to get that. Good application of your circle knowledge. Measuring an angle. How can we measure this angle? Have a go. Have a think. How could we measure it? You probably shout at the screen. Oh, my pause timer stayed on for ages then. How can we measure this? Well, you're probably telling me right now, we can't. It's just guessing at the minute. Well, no, we need a protractor. So here's a protractor. How do you use a protractor? I'm going to show you right now. So what is this measurement? This is from the latest SATs paper, by the way. You will be given access to this protractor, and we can turn it. Nice. Whoa, cool. Angles, baby. What we don't do when we use a protractor is simply just go, yeah, look, I'm going to put my angle in the A, 180. Nonsense. Here's what we do. The most important part of an angle when it comes to measuring is where the two lines meet. Right here where my mouse is. You can see it hovering. I'm moving it around. Right here. Because what we need to do is get this cross we see on the protractor to meet exactly where those two lines are. Just like that. Okay? That's the first point. But at the minute, look, do we put it here and say it's 40? Do we say it's 70? Do we say it's 170? No. Because here's what we have to do now. We have to make sure this line coming off this cross goes along one of the lines that we're trying to measure. Can you see now it's perfectly matched up? Perfectly matched up across the top line. And then we get our cross and we make sure it's right on the corner. And now that is the 2 steps to measuring an angle. Because now we start from 0 and we measure the turn. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130. So the answer to this question is 130 degrees. Now, lots of people say to me, how do I not know it's 50? Well, because 50 is counting from this 0, okay, which would be this angle, which would be angle B. No, look, we want angle A, which we can see here. So always start your line at 0. Don't start at 180, start it at 0, and then use that measurement going round. Okay, so the answer is 130. It's greater than a right angle, which we know is 90, so it has to be 130. Wouldn't make any sense if it was 50. Hopefully that makes sense to you guys. Here it is then. I love this question. I love this question. Here is an isosceles triangle inside of a rectangle. Calculate the sizes of angles X and Y. You need to know what an isosceles triangle is. You need to know the features of inside angles of a triangle and also of a rectangle. I'm going to leave you to have a go at this question. You might be thinking, what on earth do I do? Well, wait for me to go through. If you think you know, have a go first. Love this question. So, isosceles triangle. Firstly, inside of a triangle, all angles add up to 180 degrees. We've done a video on this. If you search TD Tutoring and angles triangle, it'll come up with a really cool video and proof that all the angles add up to 180 degrees. Now, why is it important it's an isosceles? Well, in an isosceles triangle, we have 2 angles the same and 1 different. So in this case, we have 30 degrees plus something equals 180 degrees. So we know that this angle X and whatever this angle is here are the same because it's an isosceles triangle. So what do we add to 30 to get to 180? Well, both of these angles must be 150 in total. Now that we know they're 150 in total, and we also know that they're the same size because it's an isosceles triangle, we can simply split 150 in half. Half of 150 is 75, which means that angle X is 75 degrees. We can put that over here. Careful, Mr. Price. Angle X over here, that means this is 75 degrees, which, by the way, unlocks angle Y. Why? Well, because in a rectangle, each angle is a right angle. And we've just talked about what a right angle is. It's 90 degrees. So this is a right angle. We've already got 75 from the triangle. What's left to make 90 in total? The answer is 15 degrees. Fantastic question. Relies on lots of geometry knowledge. You need to know angles in a triangle are 180. Angles inside a rectangle are all 90 degrees. And you have to apply that to this problem-solving question. Ultimate problem-solving question. Well done if you managed to have a go at that one. Really tricky. Oh, I like this question. I like this question because this is spatial awareness now. This is pure geometry. Can you imagine what a cube would look like, in this case a dice, if the net is folded up? On a dice, the sum of the dots on opposite faces is always 7. This is true, by the way. If you go and grab a dice, if you've got any board games or anything at home, grab a dice, opposite sides always add up to 7. So using that rule, draw dots on these empty faces to show how the dice would be made up. Remember, opposite faces always add up to 7. Have a go and I'll tell you the trick. Okay, so what we know about opposite faces? Well, look, at this one, for example, here's a 4. Now, the face opposite is the only face that is not touching the 4. It's completely separate underneath, okay? So, for example, this 6 cannot be opposite this face here because they're touching, okay? It's impossible. It can't happen. But what we do know is that this 4, right? If this 4 is touching this one here, when it's folded up, the one underneath that would be directly opposite the 4. So this 4 and this face, they are opposites. We could think about it when it comes to folding. We have the 4 here. Then next to it, this face, let's call it this one. And then look, underneath, it's all joined up. 4 blank underneath, they're opposites. 4 blank underneath. This one here must be underneath the 4. So it means that we have a 3 because 4 plus 3 is 7. Now we need to think to ourselves, okay. This 6, it's going to fold around to touch this face here. And what we then have is another one of the 3 in a row we just talked about. We have 6. Then we'd have this blank here because these two edges would meet. We'd have a blank face. And then underneath that, we'd have opposite the 6, which is this one. So this face here is opposite the 6, which means we just have a 1. And then that leaves the 2, which must be opposite whatever this one is here. And again, look, we can prove it because this edge would meet this edge. We'd have a 2, and we'd have the next one, and then underneath, this would have to be a 5. Now, lots of you are probably watching this going, yeah, easy, got that. Or you're watching going, what on earth just happened? The best way to practice this, if you have no idea what's going on, is to get a piece of paper, draw a net that looks just like this, put your dots on and fold it and see if you can see which ones would be opposite. I promise you, it's the only way to learn these questions. Make dice nets, fold it, and look and see what happens when you move them around. Best thing you can do. So here's a question then about angles. Because we've spoken about angles. I've left this to the end because I'm going to have you to have a go in a second. Stefan is facing towards F. So Stefan is facing this way towards F. Really bad line. You know what I mean. He's facing F. He turns anti-clockwise. Think about the way that a clock goes. Like this. That's clockwise around the middle. So anti-clockwise around the middle is that way. Going the opposite way that a clock does. So he turns anti-clockwise to face D. So he goes around that way to face D. What angle does he turn through? Now this is fantastic. Why? Because one full turn is 360 degrees, which we talked about earlier. He has turned from F to D. Well, what can we say about F to D? Well, that is 1/4 of a turn. If you turn your face, you can see this is a right angle right here. So 1/4 of a turn, we can prove it because he's gone through 2 letters, another 2 letters, another 2 letters, and another 2 letters. That's 4 turns. He did one of them to get to D. So it's 1/4 of a full turn. What's 1/4 of 360? Or if we simply turn our head and understand this is a right angle, we know it's a 90-degree turn. Okay? Now, the reason I solved this one is because you're going to solve this one yourself now. So Stefan is now facing towards D. We just proved that. He turns 3 right angles clockwise. Go back and have a look if you need to. What's a right angle? Clockwise. What letter is he looking at now after he's done those 3 right angles? Guys, let us know in the comments. Let me know if you enjoyed this video and what you want to see more of in the future. Like, subscribe, and share this video. It really helps us. We're putting a lot of effort into these ones, guys. So if you've got this far, please do share it and let us know in the comments below. We love reading your comments. I'll reply to as many as possible. Guys, I'll see you next time.